In this lecture, we'll derive the expressions for the potentials of the electromagnetic field generated by time-dependent sources, that is, the charges and currents that vary in time. We will find that the dynamic potentials formally look very similar to the static ones. As a reminder, the static scalar potential corresponding to a charge distribution looks like phi of r equals the integral rho of r prime d r prime divided by 4 pi epsilon naught in SI units, and here's r, where r is the distance from the point of observation and the point where the charge is located. This is essentially Coulomb's law, and a similar expression is found for the vector potential, where we have the current density instead of the charge density. As we will see in the following, the generalization to the dynamical case is surprisingly simple. In the time-dependent case, each of these expressions will be replaced by the following. Of course, now we have a time-dependent scalar potential, and then the only modification is that here we substitute the charge density at point r prime at time instance that is retarded in time, plus perhaps the solution of the homogeneous wave equation that corresponds to a free electromagnetic field. So the difference from the static case is that here the argument of the charge density is evaluated at a point in time that is in the past with respect to the point of observation by exactly the amount of time it takes light to travel from the source to the point of observation. A similar expression, of course, will be true also for the vector potential. So our goal in the rest of this lecture will be to derive these two expressions. We start with the wave equation for the scalar and vector potentials, and recall that in covariant formulation, if we pick the Lorentz gauge, which is convenient for the time-dependent problem, in the Lorentz gauge we have the identity that the Fourier divergence of the Fourier potential vanishes. That's the chosen gauge. And in this gauge, the wave equation looks like second derivative of ai dxk dxk is 4 pi over c ji. This is Gaussian units. In SI, the right-hand side is mu naught ji. If I write this equation in components, so sending I from 0 to 3 in the covariant set of indices, we'll find the two wave equations, one for phi and one for a. So they all look similar. So for phi, the right-hand side is rho over epsilon naught in SI units, and the same operator acting on a in the right-hand side has the source mu naught j. So these four equations, one for phi and three for Cartesian components of a, are all identical with different sources. The source for phi is rho, the source for a sub x is j sub x, and so forth. So the solution should have the same form, and we can just pick one of them and deal with it. So we'll pick the one for the scalar potential. Because the equation is linear, we can solve it in the spirit of the Green's function. So we can find the potential corresponding to the point charge that varies in time, and then integrate over all space. So let's consider the contribution to phi produced by the charge delta q of t equal to rho at r equals 0, delta v, where delta v is a small volume at the origin. This piece of the charge gives us the potential phi that satisfies the homogeneous wave equation everywhere except the origin. So we have this expression equal to 0 everywhere except r equals 0. By symmetry, it is quite obvious that phi should be a function only of the distance from the charge and of time. It cannot depend on the angles because of the rotational symmetry of the problem. We have a point charge at the origin. The potential has to be spherically symmetric. Thus, in the Laplacian operator, only the radial part survives, and we're going to have the ordinary differential equation for the scalar potential. So I write the expression for the del squared operator, and I drop the parts that differentiate with respect to the angles. So this is satisfied everywhere except r equals 0. Let us now make a variable substitution. Phi equals chi of r and t divided by r. We then have phi prime, where prime is the derivative with respect to r, equals minus chi over r squared plus chi prime over r. The r squared, d phi pi dr, that sits in the brackets, is then r squared phi prime equals minus chi plus r chi prime. And the derivative of this with respect to r, that's the thing that sits on the left in this equation, then becomes minus chi prime plus r chi double prime. Chi prime cancels, so that becomes r chi double prime. So the equation for chi is simpler than the one for phi. This is why I did this substitution. After cancellations, this will give us simply chi double prime minus 1 over c squared chi double dot equals 0. The dots are differentiation with respect to time. This is a simple one-dimensional wave equation, and the solution of this equation, chi of r and t, can be written as a sum of two functions. Let's call it f1 and f2. f1 has the argument t minus r over c, and f2 has an argument of t plus r over c. Here, f1 and f2 are arbitrary functions. The function f1 describes the wave traveling in the direction of increasing r, that's the outgoing wave, and f2 describes the incoming wave that travels from infinity towards r equals 0. Coming back to phi of r and t, we find 1 over r times this linear combination. Now let's see what happens close to the origin at small r. At small r, the potential goes as 1 over r f sub 1 of t plus f sub 2 of t. R over c is small, and we drop it. We also know that close to the origin, the field should look like this, like the field of the static charge. The retardation becomes unimportant when you get close to the charge. This tells us that the sum of those functions f1 of t plus f2 of t must be equal to delta q of t divided by 4 pi epsilon naught. Now let's recall the structure of the equation satisfied by phi. It is an inhomogeneous differential equation, and its solution, its general solution, can be represented as a sum of a particular solution, so some solution that satisfies the equation with the right-hand side, plus a general solution of the homogeneous equation with 0 on the right-hand side. So we can pick a particular solution of the inhomogeneous equation that is convenient for our purposes. We will pick the particular solution with the incoming wave being 0 and f1 of t then as required given by delta q of t over 4 pi epsilon naught. This is a valid particular solution. Then the solution for the scalar potential phi of r and t becomes delta q of t minus r over c divided by 4 pi epsilon naught r. Here we simply came back to this expression, set f2 to 0, and substituted the particular solution for f1. And then the argument becomes t minus r over c. So here I have delta q of t minus r over c. And in the general solution for phi, there can also be an arbitrary solution of the homogeneous equation with 0 right-hand side here. Now, let's recall what we found here. We found the potential generated by delta q, that's an elementary charge located at the origin. That elementary charge, delta q, was rho of r equals 0 dv. Now we need to integrate the overall volume, and that will give us the total potential. So strictly speaking, we found delta phi. That's the piece of the potential generated by delta q. And now we have to add them all up. The answer is clearly phi of r and t equal the integral rho of r prime t minus r over c dr prime over 4 pi epsilon naught r. Of course, there can also be a homogeneous part, and here when we integrate over the whole volume, r is reinterpreted as the distance between the charge and the point of observation. This was the result for the scalar potential, and because the equations are essentially the same for the vector potential with different sources, we have the same answer for it. These expressions are called the retarded potentials because of the retarded time argument. Let us now, to complete this lecture, work out the electric and magnetic fields that follow from these potentials. The electric field, E, is negative a dot minus the gradient of phi, and H is the curl of A. So we need to calculate these three quantities, a dot, del phi, and del cross A. The easiest thing to calculate is a dot. In A, on the right-hand side, time only enters through the argument of j. So a dot obviously becomes mu naught integral of j dot retarded over 4 pi r dr prime. The subscript retarded in the following will mean that the arguments are taken according to this prescription. The spatial argument is just the integration variable, and the time argument is shifted by R over C. Now the spatial derivatives of the potential phi or A look more complicated because R enters not only through R in the denominator, but also through R in the argument, in the temporal argument of the charge density or the current density. So for example, when we calculate the gradient of phi, we're going to have two terms. One term comes from rho retarded and the gradient of 1 over r minus r prime. That's the same kind of term that appears in the static case. But in addition, there's a term where I need to use the chain rule and differentiate first with respect to time, and that will give me rho dot retarded, and then differentiate the time argument of rho, this one, with respect to r, which will give us r divided by CR. When I put everything together, for the electric field, I'll get the following expression. So I collect the terms from A dot and del phi. So there's a common factor, 1 over 4 pi epsilon naught. There's an integral over dr prime. And there are three terms. There's rho retarded, r over r cubed, plus rho dot retarded, r over CR squared, and then I subtract A dot. So there's another term, minus 1 over C squared, R, J dot retarded. So notice in this expression that the first term here looks the same as the static field corresponding to rho. And this is what we will recover if the charge and current densities do not depend on time. Then the retardation is not important. If rho is constant in time, rho retarded just becomes rho at any time, and the time derivatives vanish, and we just get the field corresponding to the static Coulomb's law. But here we have two additional terms coming from the time derivatives. And notice that the static term and the dynamic terms decay at different rates with respect to the distance from the origin. So let's say we have charges and currents concentrated in some bounded region in space. So then the first term, as we go far away from that region, goes as 1 over r squared. That's the typical field of a static charge. But the dynamic terms goes as 1 over r. So 1 over r decays slower than 1 over r squared. So far away from the location of those time-dependent sources, the field will be dominated by these terms that depend on the time dependence of rho and j. Those are the radiation terms. They correspond to the field that carries energy away from the sources, and the flux of that energy flow does not depend on the distance because the fields go as 1 over r. The square, the Poynting vector s cross E, goes as 1 over r squared. So when integrated over a distant sphere, it will give a constant. So the fields corresponding to these terms correspond to the radiation fields. The magnetic field can also be written in a similar form. So I have 1 over 4 pi integral dr prime. And here I have two terms. There's j retarded crossed with r over r cubed. That's the static-like term, although j is retarded. But then there's a term coming from j dot. G dot retarded crossed with R over C R squared. So again, just as for the electric field, there's a field that looks like magnetostatic, if not for the retardation, and then there's a radiation part that goes as 1 over R. So these two equations for the fields, they're called Jefimenko equations. Again, please make sure to note that in contrast to the expressions for the potentials that look very similar to the static versions, with the exception for the retardation in the time argument, the expressions for the fields do not look like the retarded versions of the static fields. The retarded versions of those would simply look like the first terms here. There are additional terms that decay as 1 over R that correspond to the radiation fields. This concludes this lecture on the retarded potentials.